Hello everyone. Welcome to the week 10 of the problem solving session for the course Differential Equation for Engineers by Professor Srinivasa Manam at IIT Madras. And I am Priyanka Agarwal, a PMRF scholar at Indian Institute of Science in the Chemical Engineering Department at IISc Bangalore. And so I'm here to solve some problems, initial boundary value problems for the wave equation today. We will look at some problems and try to find the solution using the concept which has already been taught in the main lectures. So let's see a question where we have to solve the initial boundary condition. Solve the initial boundary value problem. And the problem is utt minus 4uxx equals to 0 and the domain is 0 to x to infinity, that is the semi-infinite domain for all times greater than 0. Now the conditions which we are given are u at x t equals to 0 is x4. So for these, for all x this is valid, and u t at x comma 0 is given as 0. So these are our initial conditions. And then we are given the boundary value problem. Since this is a semi-infinite domain, we only know the condition at one of the boundary. So u at 0 comma t, that is at x equals to 0, which is, we are given that u is 0 for all t greater than equal to 0. So now we have to solve this problem, initial boundary value problem. So clearly this problem is semi-infinite string with a fixed end. So it falls in this category, and we see that this x to the power 4, so we can call it as f of x, and this we can call it as g of x. So if I take you to the last tutorial session, we have already seen this thing, that if we are given the initial conditions at these initial conditions for the wave equation, then we can solve it using applying this transformation, which is D'Alembert's solution, and then the wave equation reduces to this form, and the general solution can then be written in terms of xi and neta, and therefore this is the general solution which we get. Okay, now coming to this, so since we know that this is semi-infinite string with a fixed end kind of a problem, we can solve this problem again using D'Alembert's law. So we can apply the transformation x minus ct, which is equal to xi, and neta is x plus ct, and then we get u as a this is the general solution, and x minus ct plus ct, x plus ct, and what we know is that the final solution, if we write C1 and C2, just from this uh, equation we can directly reach this. So then u of x comma t can be written as 1 by 2 f of x minus ct plus f of x plus ct. Okay, and the other function, if you see, you know very well. See, I'll just refer back to it that gs is 0. So just for the sake of completion, I shall write it. Otherwise, we know that what is 1 by 2c integral x minus ct to x plus ct gs ds. So this is 0. So we are only left with this function u x comma t equals to 1 by 2 f x minus ct plus f of x plus ct. And you see over here the equation is utt minus 4uxx equals to 0. So this implies that over here c is equals to 0 and also f of x is equal to x to the power 4. Therefore, for x plus ct, right, greater than x plus ct x minus ct greater than 0, the solution will be u x comma t equals to 1 by 2 x minus ct to the power 4 plus x, c is 2 here, so x plus 2t to the power 4. And for x plus ct, for x minus ct greater than 0 is this, and for x minus ct less than 0, the solution will become 1 by 2 x plus 2t to the power 4 minus x minus 2t to the power 4. So this is the case of even function, right? Since x to the power 4 is even function. So these cases also we have seen in the last lecture, and I will just take you to the step where we have shown this in the last tutorial session. So if you see this thing, for even function we have this form, right, for x less than ct, and this is for x greater than ct, while we have this for the odd function. This becomes ct minus x. Let's keep it in the conventional form, although it won't matter much. But let's write it as ct minus x only, so 2t minus x. So we clearly know that this is for x greater than 2t, for x greater than 2t, and this is for x less than 2t, right? Okay. Now we know that u 0 comma t equals to 0, which is this boundary condition. So in this case, if you just put x equals to 0, what's the solution which we get? So if you see, you have to check this. Okay. Now for x less than 2t, okay, that means that 0 less than 2t, that means t greater than 0. Now for this boundary condition is what we have, right? So for this case, this is the solution, and we see that u x comma t is equal to 0 in this case. Hence we can say that this is satisfied for x less than 2t, which implies for t greater than 0. Now the other case is x is greater than 2t, which means t will be less than 0 if we put x equals to 0 here. And for this, of course, the condition is not satisfied, right? Because, and also this is not in our interest. Okay. Now let's solve another question. So we have to solve the initial boundary value problem. Initial boundary value problem. Where we have this problem utt minus uxx equals to 0, and u of x comma 0 is 0, and u of t x comma 0 is x cube, and ux at 0 comma t equals to 0, and this is for t greater than or equal to 0, and all this is for semi-infinite domain. Okay, so both these are valid when x lies between 0 to infinity. So now we have to solve this problem. So again, this problem is of the type semi-infinite string, but with the free end over here. It's not fixed. Last time it was fixed. So now if we just see over here, c equals to c square is 9, so c equals to 3. From this, utt minus c square uxx equals to 0. So by comparing, we get that c is equal to 3. And then our fx is 0, and then our gx is x cube, right? So if we write using the algebraic solution, so the first part will become 0, the part which is containing fx. So ux comma t can be written as half of f x plus ct plus f of x minus ct plus 1 by 2c integral x minus ct to x plus ct g of s ds. Now this part should become 0 because f of x is 0. So we are only left with this thing. So let's say x minus 3t. If it is greater than 0, that is the case when x is greater than 3t, ux comma t can be written as 1 by 2 into 3 integral x minus 3t to x plus 3t. Now you clearly see this is an odd function. Okay, so now this becomes s q d s. If you solve it, this is 1 by x, s to the power 4 by 4, and the limits are from x minus 3t to x plus 3t. Okay, hence this becomes 1 by 24 x plus 3t to the power 4 minus x minus 3t to the power 4. Okay. Now for x minus 3t less than 0, that is x is less than 3t, what we have is ux comma t equals to 1 by 2 into 3 to integral 0 to x plus 3t s cube ds plus, then we have this 3t minus x, no? So x minus 3t. So this integral is x minus 3t to x plus 3t, right? But in this case, since it is an odd function, so we can break this integral into 2. So we can actually write it as x minus 3t to 0 and then 0 to plus x plus 3t, right? And then if you see, this is 1 by 6. This becomes, so this is actually now not s minus s. So now to be change the sign changes here. This minus, let's say, it comes out, and then this if we take it in the integral reverse. So this will become s cube ds See, in this case, this is less than 0, so we have to make it a positive value. And to make it a positive value, we can write it as 3t minus x, the minus sign. And then the limits will also get reversed. So this is now 0 to 3t minus x s cube ds. And this then becomes 1 by 6 s to the power 4 by 4, the limits are from 0 to x plus 3t plus s to the power 4 by 4, and their limits are 0 to 3t minus x. Okay, so this becomes 1 by 6 x plus 3t to the power 4 over 4 and minus 0 plus 3t minus x over 4, and this raised to the power 4. So this becomes 1 by 6 into 4. So we can directly write it as 1 by 24. So 1 by 24 x plus 3t to the power 4 plus 3t minus x to the power 4. So this is the solution for the case when x is less than 3t. I hope it's clear to everyone. Now we have to apply this condition that ux at 0 comma t is 0. So for t greater than 0, as we saw in the previous case, x should be less than 3t, right, at x equal to 0. So for this case, the solution is ux comma t is equal to 1 by 24 x plus 3t to the power 4 plus 3t minus x to the power 4. So boundary condition, what we have is ux at x 0 ux at 0 comma t is equal to 0. So if we just write ux, what will it be? 1 by 24. This becomes 4x plus 3t cube and then minus 4 3t minus x cube. So I just differentiated it once. So this is now 1 by 6 x plus 3t cube minus 3t minus x cube. Now if you see ux at 0 comma t, it is 0 means satisfied. So this is our required solution. So we can also solve other problems which fall in this category similarly. But now just let's move on to another problem. Now the question is, solve the signal problem governed by the wave equation. Which is utt now equals to c square uxx. Okay, where x is greater than 0 and t is greater than 0. And initial condition, u at x comma 0 equals to ut x comma 0 equals to 0 for all x greater than 0, and boundary condition is u 0 comma t equals to some velocity which is a function of time at t greater than 0. Okay. Now we have to solve this particular problem. Okay, so let's apply the transformation. xi equals to x plus ct and delta equals to x minus ct. Okay, and when we apply this condition, what we the general solution is ux comma t is c1 x plus ct. From this this equation becomes this, and this is the solution which we get, x minus ct. Now this is the general solution. Now let's apply boundary condition. Which is ux comma 0, sorry, initial condition x comma 0 is 0, which implies that c1 plus c2 equals to 0, and we have this ut x comma 0 equals to 0, which implies that with respect to time to differentiate, we will have this c outside and then c1 prime plus c, and now we have minus c outside and then c2 prime equals to 0. So that is c1 prime minus c2 prime equals to 0. Here we have to draw cs comma. Okay. Now we have to solve these and get the solution for the general solution, which is ux comma. So we have to find that solution. So in this case, if you see what is c1, c1 is minus c2. So we just change the color so that it's clear to you. And then c1 prime equals to minus c2 prime, and then it becomes c1 prime plus c2 prime equals to 0. So this is our equation 1, and this is our equation 2. Then what is the solution? It's c1 prime plus c2 prime equals to 0, and c1 prime minus c2 prime equals to 0. So c1 prime equals to 0 and c2 prime equals to 0, right? So this is what we get, correct? That means c1 is some constant, c2 is some constant. Okay, but now let's see by applying boundary condition. Now if you apply boundary condition, which is that at u0 comma t we have some u. So this will become c1 of minus ct, sorry, plus ct plus c2 of minus ct equals to some u of t, right? Now for this is for t greater than equal to 0, that means x less than ct. Right? And if we just replace minus ct by x minus ct. What do we get here? So we are replacing minus ct by x minus ct, okay. So now this becomes c2 x minus ct equals to u of t can be written as now t minus x by c and then minus c1 ct minus x. Okay. Now since what we know is that c1 of x equals to 0, then what we get, c2 x minus ct is equal to u of t minus x by c. Okay. And therefore we have u x comma t equals to 0 for x greater than ct, and it is equal to u t minus x by c minus c1 ct minus x for x less than ct, and therefore we have u x comma t can be written as u into t minus x by c and as a Heaviside function. So here this h is the Heaviside unit step function. Okay. Now there could be also another case now let's just end this problem here and solve another problem. Where we have to find the solution of the initial boundary value problem which is utt equals to uxx and x lies between 0 to 2 and t is greater than 0. Okay. And we have to x comma 0 equals to sine of pi x over 2 0 to 2 and then t with x comma 0 equals to 0, which is u x into, and then we have this 0 comma t, which is the boundary condition, and another boundary condition we have is 2 comma t equals to 0 for t greater than equal to 0. So these two are the initial conditions, and these two which we have are boundary conditions. And now we have to solve this particular problem. Now clearly, so this problem is of fixed end. So if we have to solve, so this problem is vibration of finite string with fixed ends. Okay. So the transformation which we apply is always xi equals to x minus ct and beta equals to x plus ct, and c is 1 here, right? Then xi equals to x minus t and beta equals to x plus t, right? So this is what we have been doing so far, and this will be our function fx, and this will be our function gx, for writing the solutions in form of the D-D'Alembert solution, right? Now, how can we write the solution then? So let's just individually see. First, let's see the general solution, which is ux comma t can be written as c1 of xi and plus c2 of beta. All these can be written interchangeably, that doesn't matter. Right, so c1 so let's write this as C and this is C. So C1 of xi we'll have to see the convention, and the convention says this thing out here. We write C1 as xi, which is x minus Ct, and C2 as x. So by sticking to this convention only, we have C1 xi, C2 beta, and C1 of xi can be written as 1 by 2 f of xi plus, in this case we can write this plus k by 2. So basically we are writing that g part, we can write it that 1 by 2 c summation of all that. So now just let us represent it by capital K by 2. So this becomes 1 by 2 sin pi zeta over 2 plus q by 2 for xi between 0 and 2. And similarly, we can write c2 beta as 1 by 2 function meter f of meter minus k by 2, and this can be written as 1 by 2 sine pi meter over 2 minus k by 2, and then this meter is also between 0 to 2. Now, using the boundary conditions, we get C2 of meter equals to minus the C2 of meter equals to minus C1 of minus meter. See how the boundary condition says we have u of this equal to 0. So what do we have? C1 C1 of xi, if we just put it x equals to 0, then it becomes minus ct plus c2 of ct equal to 0. So this can be written as 1. See, when solving these kind of problems, we don't have to apply this transformation exactly. Actually, we do have to apply this transformation only. Okay, sorry for creating confusion. Okay, so now we have this which can be written in this form, and once we write it in this form, then what do we have here is that this is equal to minus 1 by 2 sine minus pi meter over 2 minus k by 2, where minus meter is between 0 and 2. Okay, and similarly we just write C1 of xi, we have minus xi 2l minus xi, C2 2l minus xi. Okay, and when we have this becomes minus 1 by 2 sine of 4 minus xi over 2 into pi plus k by 2. And now this 4 minus xi is between 0 to 2. Okay, and then this becomes 1 by 2 sine pi xi over 2 plus k by 2. The pi is now equal to 4. Okay, now if we proceed in this manner, the solution can be determined, which becomes 1 by 2 sine pi times x plus ct over 2 plus sine pi x minus ct over 2. So this is the final solution. Okay, and let's look at one more problem of a non-homogeneous boundary value problem for wave equation. So the question is, determine the solution of initial value problem. UTP minus C square UXX equals to some X plus CD, and we are given that initial value problem Ux equals to X and Ut at X comma 0 is sin X. So this is the problem. Now to solve this problem, we know that this is now non-homogeneous wave equation. And therefore, so for non-homogeneous wave equations, if let's say they are of the form they are of this form where it is given UTP minus C square UXX equals to some non-homogeneous function X comma T. Okay, then the solution which you get over here, so you use transformation y equals to C2 and you find the solution, and solution is of the form 1 by 2 integral x minus y to x plus y, or I will just write Ct g star of some function is ds plus 1 by 2 f x plus Ct plus f x minus Ct plus 1 by 2 c square integral over the region x star x comma 2 dr. This is over region R, where h equals to minus h star over c and g equals to g star over c. Okay, so this is the problem. Okay. So now we have to first substitute in this particular equation. So now our solution will be mu x comma t equals to 1 by 2. So in our case, if you see, so this is fx and this is g and this is h. So let's just write it down first. So we have f of x equal to x, g of x equal to sin x, and h of x comma t equals to x plus ct. Alright? So now h star becomes minus c times x plus ct, g star becomes c times sin x. Alright? So now this solution becomes u x comma t equals to 1 by 2c dy x minus ct to x plus ct sin s ds plus 1 by 2. This will be just x plus ct plus x minus ct and then plus 1 by 2c square 0 to ct, and we have this then this y plus x plus ct. So y plus x minus ct to minus y plus x plus ct, x plus ct dx dy. So here the transformation is that y has been chosen as ct. Okay. So now this becomes so for this cancels and this becomes x plus 1 by 2c minus cos s, and limits are from x minus ct to x plus ct. Now for this we have 1 by 2c square 0 to ct, then this becomes x square by 2 plus ctx, and the limits will be from y plus x minus ct to y plus minus y plus x plus ct dy. So we have integrated with respect to x first. Then this becomes x plus not x plus 1 by 2c minus 1 by minus x minus 1 by 2c cos x plus ct minus cos x minus ct plus 1 by 2c square 0 to ct. Then what does this becomes? Minus y plus x plus so we have to substitute this plus ctx so here we have to put this condition, and this will become, if you solve, one by 2c square x ct minus 5 plus minus y plus 2 ct dy. Okay, because here there is no y term, So this becomes, so it becomes this thing, and then we have x. So this can also be expanded, cos a plus b minus cos a minus b. So it is cos a cos b minus sin a sin b. So this way cos terms would get cancelled, and then we have this uh, minus sign with sin terms. So this is now x plus this will be then sin x sin c2 over 2c plus 1 by 2c square okay. So sin will cos a cos b minus sin a sin b. Then this will be minus cos a cos b plus sin a sin b. So that plus would become minus, so minus minus it becomes plus, and then what we have is 2 sin a sin b over this 2c plus 1 by 2c square, and then this particular integral, which becomes x ct into y minus y square by 2 plus minus y square plus 2 ct y limits with 0 to ct. So this becomes x plus sin x sin ct over c plus 1 by 2c square, and this becomes, when we put ct in place of y, so this for 0 it is 0, so for ct it becomes x ct square minus ct square by 2 into x minus ct square plus 2 ct square. So this becomes x plus sin x sin ct over c plus 1 by 2c square 1 by 2 x c square t square plus c square t square, and then this becomes x plus sin x sin ct over c square gets cancelled, so this is then 1 by 4 x t square plus 1 by 2 t square. Okay, so this is the general solution between x, t. So I hope you had some understanding for how to solve the questions given in the assignment. And if you have any doubts, please let me know. I will wait for a minute for your doubts. Okay. If there are no doubts, then we will close the session here. Thank you for joining me and see you next week. Thank you. Bye bye.